So we sometimes call these size as potential functions, right. So psi c is a potential function associated with the clique C, right, and x c is the set of variables that are participating in clique C, right. So it is a product over all of these cliques, okay. There is a small problem here, right. So we have to make sure that whatever we are writing is a probability function, right. So how do you make sure of that?
Integrate it overall and divide by the number.
Right. So you basically have some kind of a normalization factor where z will essentially be whether the integral or the sum or whatever. If you are looking at discrete valued, we have been talking about binary stuff so far, right. So if you are looking at binary valued variables, so essentially this will be sum over all values that x can take, right. Suppose you have n binary variables, the sum will run over 2 power n entries, right. Sounds like a really bad idea, right. Anything wherever you are summing over 2 power n elements seems to be a bad idea, and it is. So the biggest difficulty in using undirected graphical models. So why didn't you have this in the directed graphical models? We chose the factors cleverly, right. The factors were chosen to be conditional distribution. So when you took the product, it was guaranteed to be a distribution. But here we have no such restrictions on the size, right. So this is what makes it even more confusing. I have no restrictions on the size. Psi can be anything, right. Psi can go run up till 3 million. I don't care, right. So psi can be any function, right. Psi can become negative. Oops, can it? No, right. The only condition I have is psi has to be non-negative, right. Yeah, okay, that is a good question. Does psi have to be positive or non-negative? Non-negative, right. So it is okay for me to have 0 probability for some configuration, right. So psi can be so if psi is non-negative, then that is all the condition I need. So the only condition I need is that so for all values that xc can take, psi has to be non-negative, right. So z is also sometimes called the partition function, which is a terminology that comes from physics, right. So I am not going to get into the explanation of it, but sometimes also known as the partition. So if you are reading up something and somebody mentions partition function, okay, it is essentially the z that they are talking about, okay. So that makes it a little tricky, right. So we are saying that your this thing is not restricted in the interpretation, right. Your so psi c is not restricted in interpretation, it can be anything, and as long as you can do this normalization, you will get a probability, okay. So I am going to write down a very powerful theorem. Right. So the Hammersley-Clifford theorem or the Clifford-Hammersley theorem, it says that for any probability distribution, right, for any probability distribution that is consistent with this kind of a factorization over a graph, right. So any probability distribution that is consistent with this kind of a factorization over graph, right. The condition here is a little stricter. So the condition says that right, it can't be 0, right. So the condition says it has to be positive, not non-negative. So what the Hammersley-Clifford theorem says is, if a probability distribution okay, that is consistent with this kind of a factorization, that is, I mean, if such a factorization exists, okay, then that probability distribution can also be expressed by using factors that are of this form. So that makes our life easier. So then now my energy function, or what the E function is called the energy function. So all of this comes from physics, right. So you will see all this energy and other things here, energies and potentials, you will see that. So the energy function, right, can be anything now. So there is no restrictions, it can be negative, it can be positive, right, well, as long as it is real, I suppose, not complex, right. So the energy function can be anything. So this is known as the right. So essentially what the Hammersley-Clifford theorem tells us is that, so if you write your probability as a product of exponentials, right, of say these kinds of factors, okay, then there exists a graph representation where this kind of a factorization can be obtained. And likewise, if you are able to write a factorization like this on a graph, then you can have it is expressed as a product of exponentials, right. So each factor is an exponential, so essentially my probability will be the product of exponentials, right. So this is actually a very powerful result because it allows us to simplify a whole bunch of computations, right. I do not have to consider any arbitrary form for my psi, right. So immediately you see this, right, I do not have to consider an arbitrary form for psi, it is just an exponential, okay. Now I have to consider an arbitrary form for my energy, but now that we started talking about it as energy, so we can start applying our intuitions from physical systems, right. So what should be a state with a high with a high probability? Exactly, we know that, right, a state with a high probability should have low energy. So when you start looking at the data, right, I find that configuration XC which is most popular, most prevalent in the data, right, and I am going to assign that the least energy, right. I do this for every click, see, the power of nomenclature. So I call it energy, and now everybody understands what the graphical model is doing, right. So if the energy is very high, so it is going to be e power minus the energy, so the probability is going to be low, or rather this factor will be low, right, and this psi c is going to multiply here in your numerator, right, therefore the probability that you assign will be low, right. If the energy is very low, the e power that will be high relatively, right, and therefore the probability you will assign will be higher. So that is essentially what we are going to do, right. So as far as undirected graphical models is concerned, so how do you decide what this energy function should be? It depends on the prevalence of that particular configuration in the data, right. So what will be the energy of x1 is 1 and x2 is 0 and x3 is 1, okay, how often did that combination occur in the input, right, and what should I do with that? Nothing, I can just use the count as the energy, right, because energy is unrestricted, I do not have to worry about normalizing it or anything, right. I just use the count as the energy for that count in the data, I can use that as the energy. So the higher the count, the higher the energy, and therefore more prevalent the more probable that configuration will be. Sorry, higher the count, okay, then 1 by the count is the energy then, yeah, use 1 by count as energy, right. So the higher the count, the smaller the energy, and then the more likely the configuration will be, right, sorry, yeah, right. So that's easy enough to do, right. So I wanted to look at, before I go on to do some inference thing, I want to look at one at least or two popular graph can be at most 1, yeah, so this can be 0, so that can be at most 1, yeah. Anyway, we are interested only doing probabilities here, right. So that is not that much of a problem, right. Yeah, that meant again that is the beauty of the Hammersley-Clifford theorem, that's essentially it, right. It tells you, hey, yeah, it is fine, you still can represent any probability distribution you want by looking at it as product of exponentials, right. So that is the thing. I will leave this. since all of us now understand undirected graphical models, I will start with the simple undirected graphical model, right, and right. So this kind of a simple lattice like structure, right. So undirected graphical models are also sometimes called Markov random fields, just like directed graphical models are also called Bayesian networks, right. Undirected graphical models are also called Markov random fields, right. So people, if you have heard of the term Markov random field somewhere, right. So one of the most often used structure in the with Markov random fields is like this kind of a lattice structure. Okay. So what does this really tell you? It tells you that this variable, okay, is independent of everything else in the network given the 4 neighbors, right. Then this variable is independent of everything else in the network given only these 2 neighbors, right. I mean these lattices can run for like 32 cross 32, or sometimes 256 cross 256, right. People typically use these kinds of lattices for modeling images.
Sir,
Right.
why is it called Markov?
Okay. So it's random, you agree with that, right? Right. So all of these are random variables, right. So I have this collection of random variables. Okay. It's called Markov because in this particular case, right, given the immediate neighbors, right, I am independent of everything else. Right. So if you think of what the Markov assumption is in probabilistic models, right, so stochastic models, the Markov assumption says that given the immediate predecessor, you are independent of the past, right. So that is a normal Markov assumption, right. So given the immediate predecessor, you are independent of the entire in the past. So here what I am saying is instead of the predecessor, because there is no notion of direction here, so there is no predecessor here, so instead of that I am saying given the immediate neighbors, I am independent of everything else. That is why it is called Markov, right. So let us take xi, right. So xi is independent of everything else given right. So now what people do is they try to use this for making all kinds of predictions, right. So I am interested in labeling every pixel in an image. So I have a big image, right. I want to label every pixel in an image. Give me an image labeling task. I want to label every pixel as either foreground or background, right. Is it the guy standing there or is it the tree behind him, right. So I want to label it as foreground or background, right. So now it is a 2 label task, right. So each of these random variables will take one of those values. What are the values it will take? It will take whether it is a foreground or it is a background, okay. Now here is the additional assumption I am going to make. I am going to make the assumption that the value of the pixel I am going to see, okay, the value of the pixel I am going to see depends on whether it is a foreground pixel or a background pixel, right, nothing else, right. The value of the pixel I am going to see depends on whether it is a foreground pixel or a background pixel and nothing else, right. So essentially what I will do is I am going to assign more random variables, right. Each one of them stands for an individual pixel, okay. Each one of these stands for an individual pixel. So now what will I do is I will observe these pixels, right. I initially will observe the pixels. So what will be my potentials here? What are the size? How many size do I need? One for each edge, right, because that is the maximal clique here. I can't do anything better than that. So for every edge in this graph I will need a psi, right. For every edge in the graph I will need a psi, right. So what I will do is I will observe these pixel values, okay. So some values I will observe, okay. Then what I can do is I can figure out, okay, what should be this label of this pixel, right, just with this knowledge alone, right, because of there is this potential, right, I can kind of convert that into a potential on the node alone. You see that, because I have observed the values for the pixels, right, I can essentially take that entry from that thing, right. So there will be one column associated with that pixel value, right. So people are giving me blank stares. We are talking about a function of two variables, right. So I will call this xi, I will call this yi, the pixel value xi yi. So I will tell you what yi is, right. Then what will I be left with? A function on xi, right. If I tell you what yi is, I will be left with a function on xi, correct. So I can convert, given an observation, right, I can convert these potentials, right, into potentials on xi alone.
Yi's are also the part of graph.
Yi's are part of the graph, but the way I use it will always be that I am given the yi. So here is an image, give me the labels, which is the foreground, which is the background. So I will always know this yi's, right. So given the yi, I can convert this edge potentials into node potentials, right. So this is essentially now I from the function of xi yi, it will become a function of xi alone, okay. So if you look at many such I mean graphical model applications, right. So you will actually find that they will always reduce this into node potentials and edge potentials. So it will look like they are defining something called a node potential, okay, which is like a potential function on single variables, and then they will be defining edge potentials, which are potential functions on pairs of variables, okay. In reality something like this would be happening for you to assign node potentials, okay. The node potential are essentially marginal, some kind of information you have about the marginals, okay. So in this case I am telling you how the marginal information comes. It is not complete, it is not the complete marginal, okay. Given the pixel you can make some guess about what the xi should be, so that is my node potential. So I can reduce all of these edge potentials between a node and a pixel, okay, between a label and a pixel I can reduce it to a single potential on the label, right. So now having done that, right, what can I do? So there will be some potential for a label here, okay, there will be some potential for a label here, right, and there will be some potential for these two labels happening together, right. So essentially this is telling you, okay, this is a background, okay, what is the likelihood that this is also a background? If this is a background, what is the likelihood this is also a background? Okay, if this is the background, what is the likelihood that is a foreground? So like that, right. So for each of these edges, so I have where the edge can change, where the label can change, that information I have, right. So finally when I assign the final labels to this, so what will I do? I will find that configuration of labels, okay, that gives me the lowest energy, right. Essentially that would mean that this potential should be low, right. If so suppose this I say is background and this I say is foreground, then when I say label is B here and label is F here, that entry in the potential function should be low, right. People get that? So that entry in the potential function should be small. So like that I need to do this for all the pairs here. So it is a very hard problem, so because it is severely constrained, so I have to consider all possible pairs and I have to figure out where the low entry occurs across this pair. So for example, so if I say this is background and this is foreground, I say B and F and this gives me a low value, right, but I say B and B for this and this gives me a high value, right. So I can possibly turn this into an F, right, but then the whole thing might come around and then this might get changed back into an FB, right. So then I might go around and around. I have to figure out what is the right potential to pitch this, and that is the inference problem. So inference problem is really hard in the undirected case, right. So in so much so that when you have loops like this, right, when you have loops in the graph like this, exact inference is impossible. To actually give you the right answer is impossible, right. Quite often we end up giving some kind of an approximation, right. So where can you give exact answers? when there are no loops, right. So an undirected graph with no loops is a tree, right. So on trees you can give exact computations, but as soon as you have any loops in that, then you have to do some kind of approximation, right. There are some very special cases, but we will not go there, right. I just want you to get an intuition of what the individual factors would mean, right. So how will I determine what these factors are? Okay, so let us look at this, right. I want to look at that guy, right. So what am I going to do? Right, so what does it really need? So I want to assign a low energy to the configuration that occurs most often in my data, right. So what I will do is I look at the label data. So I look at each pixel's label, right. The label data will tell me which pixel is foreground, which pixel is background, right. Then I look at for these two pixels in the image, let us say I have only a 3 by 3 pixel image, right. But for each of these two pixels I look at them, right. I will figure out, okay, how often was this foreground and this also foreground, how often was this foreground and this background, how often was this background and this foreground, how often this background and this background. So all these 4 things I will look at, I will just count that from the data, and then I will set the energy to be some inverse of that, the count. So the one with the largest count will get the smallest energy, right, pretty simple, right. So like that I can do this for each and every thing, right. So that's one thing. So the second thing I will have to do is then start looking at this thing.
There be a psi function for xi and yi.
Yeah, exactly, that is what I am saying, that is what I was pointing out, sorry, so you are looking at my back, you can't see from there. So I said there should be a potential function for xi and yi as well, right. So what I will do, I look at the data again. So I look at, okay, when the pixel value was this, okay, what was the label, right. So I will do that, I will do the co-occurrence information, okay. Now things should start looking a little fishy to you guys, right. I mean the pixel can have a lot of values depending on how I am encoding my color or brightness or something like that, right. So that I could end up having a very large distribution there itself, right. So even if you assume that my pixel is going to have 256 levels of brightness, right. So for every value, so there is 512 probability, 512 counts that I have to make, right. 512 counts looks suspicious, right. Will I have data to actually make accurate estimates of 512 individual counts? Well, I could if I have very large volumes of data, but typically what you do is you don't, for yi you don't do the explicit counts like this, right. You try to learn the factor yi by some kind of a parameterized function, right. So you could use logistic regression, right. So figuring out what's the probability of xi given yi, right. That logistic regression can tell you, right. So you encode your pixel using whatever things you want, right. So you can look at, you can do even more funny things, right. You can do funky things. You can make this a function of all of these pixels, right. So that, of course you are moving away from your Markovness, but once you start thinking of doing logistic regression you can come up with very powerful classifiers, right. So typically the yi xi probabilities, right, or the yi xi factors are learned in a different manner. They just don't do the maximum likelihood estimate, you do some other thing, right. Typical, like the most popular choice is using logistic regression, right. You can do other things, but then the xi potentials you can learn in using maximum likelihood estimates, simple maximum likelihood estimates, provided they are small enough, okay. So that is basically how you train this Markov random field, and it turns out that they are pretty powerful in terms of working with images and in a very wide variety of settings, right. And people use MRFs a lot, right, and there are variants of it which is called conditional random fields, so people use those also tremendously. So yeah, very popular and powerful classifier, and training it can be a pain, right. So I just gave you a simple example, right, where you just did the counting and stuff like that. When you have a very large model, right, very large graph, right, training it can be a pain, but then people because the data is sparsity, right, so I have to look at all possible combinations of all variables, right, and so it becomes a little tricky, and so you have to come up with clever ways of training the models. Okay, it's particularly this part of it that's painful, right, not size not completely determined, it's just that the inference process is hard, like I was telling you, right, you may keep going in circles, it may take a long time for you to actually converge to a probability and so on and so forth, yeah.
But it can find.
Yeah, so that exists a proper assignment to this, so that yeah, so but finding it is hard, yeah. The Clifford-Hammersley tells me that no, I am not worried about loops, right, so as soon as I say click there is a loop.
But for a click you assign only
Sorry?
1 year. For a click you assign only 1 year of
Yeah,
extra.
one potential, yeah.
So click has loops.
The click has loops, but it's only one potential, right, so it's fine, I will be doing the inference on that potential alone, I won't get into this loop business. So the loop business started off saying that okay, I will make one inference, one assignment here, one assignment here, one assignment, but if this had actually been a click, right, then I will know what is the combination of assignments to these 4 variables that has the lowest potential, I would have just done that, right, so I wouldn't have to run around chasing the things, so that's the thing, right, so. But I still have to do the chasing around because this has other things it's involved in, right. So the only way I can ensure that I don't do the chasing around is if I have one connected graph, complete graph, right. So if I have a complete graph, then of course there is no chasing around, and then what's the difficulty?
Number of combination each one.
There is no factorization. I am back in the original thing. I mean, I as well not have worried about the graph, right. So if I have a complete graph, there is no factorization. Right. So, but that is the only way I can ensure that I will not get into